At the heart of a crowded stellar nursery in the Large Magellanic Cloud, one star pushes the very limits of what a star can be. R136a1 is so massive, so luminous, that it challenges our understanding of how stars are born, how they live, and how they die. Its radiation sculpts the surrounding nebula, and its gravity dominates a cluster of already extreme suns. Today, we explore what makes this record-breaking giant so extraordinary, and what its existence means for the life and death of stars. If you enjoy journeys to the most extreme objects in the cosmos, please like, subscribe and share, and tell us in the comments, what would you ask about a star this massive? Thank you for watching. Now let's begin. Deep inside the Tarantula Nebula near the centre of the Large Magellanic Cloud, a single dense swarm of young stars forms the compact system known as R136. In this region, the usual dark spaces between stars almost vanish, because the cluster gathers thousands of suns into a volume only a few light-years across, turning the local sky into an almost unbroken field of light. The Large Magellanic Cloud itself orbits the Milky Way as a small companion galaxy, but the stars of R136 belong firmly to the Tarantula's core, where gas and dust are already carved into arcs and cavities by the combined energy of their radiation. From a distance, images taken with large telescopes show a bright knot at the heart of the nebula, and careful study reveals that this knot is not a single object, but a tight gathering of the most massive and luminous stars known. R136 is often described as a superstar cluster, a very compact and massive stellar system that may one day resemble a globular cluster after its gas is cleared and its most massive stars leave the main sequence. For now, though, it remains a very young assembly, only a few million years old at most, with almost all of its most luminous members still in the short, intense early stages of stellar life. Because the cluster is so distant, astronomers once saw it as a single blurred light source, and could not separate its individual stars. As telescope technology improved, especially with the Hubble Space Telescope and large ground-based observatories using adaptive optics, the central light began to resolve into many distinct points. Within a region only a few light-years across, there appear scores of very hot blue-white stars, many of them of spectral types associated with the highest masses and temperatures. Their combined light provides most of the energy that makes the Tarantula Nebula glow so strongly in hydrogen emission. The radiation they emit, especially in the ultraviolet part of the spectrum, ionizes the surrounding gas-stripping electrons from hydrogen atoms and causing the nebula to shine when those electrons recombine. The cluster's mass is enormous for such a young system. Estimates suggest that R136 contains the equivalent of hundreds of thousands of solar masses in stars concentrated within a small central region. This extreme concentration means that an observer placed inside the cluster would see hundreds of bright blue stars spread across the sky, each one much more luminous than the sun, and the concept of a dark night would hardly apply. The stellar density also means that interactions between stars and their gravitational fields are relatively common on astronomical timescales, and such a crowded environment may have influenced how its most massive members assembled. Yet despite this, the cluster as a whole still behaves in a regular gravitationally bound way, with stars moving under their mutual attraction in orbits that respond to the total mass of the system. The age of R136 can be read from the types of stars present. The cluster contains many very hot luminous stars that still show signatures of hydrogen burning at their cores, and it lacks cool evolved supergiants that would signal an older population. Models of stellar evolution indicate that such a mix corresponds to an age of roughly 1 to 2 million years, which is extremely young in stellar terms. At this age, even the most massive stars have not yet had time to end their lives as supernovae, so the cluster is lit by an intact population of extreme stars, whose energy has only begun to shape their environment. Because many of these stars are both massive and very hot, a significant fraction of them produce powerful stellar winds, streams of gas flowing outward at high speed. When the winds from many stars inside a compact cluster combine, they fill the central region with hot rarefied plasma, pushing on the surrounding nebula gas and helping to clear cavities around the core. This collective outflow contributes along with radiation to the feedback that regulates further star formation in the Tarantula Nebula. In this way, the cluster is not a passive collection of stars but an active engine that affects the structure and evolution of its parent cloud. Observationally, R136 poses a challenge because of its distance, the crowded nature of its core, and the obscuring effects of dust along the line of sight. Astronomers must correct for the way dust reddens and dims the light from the cluster, and they must use high spatial resolution to separate individual stars that lie very close together on the sky. Spectroscopic measurements which spread the light of each star into its component wavelengths are needed to determine temperature, surface compositions, and wind properties. In such a crowded field, spectra of neighbouring stars can overlap, so data reduction and modelling require careful work. By combining images and spectra, researchers can build a census of the most massive cluster members and estimate their individual luminosities and masses. The sum of these properties then helps define the overall mass, luminosity and energy output of the cluster. Within this central swarm, several particularly bright points stand out as the most luminous and massive stars yet identified. But in this first view of R136, the focus remains on the cluster as a whole. It acts as the wider stage on which those individual stars reside, providing the gravitational framework, the shared radiation field, and the hot wind-filled medium that surrounds them. The existence of R136 shows that nature can assemble very massive stars in compact, intense star-forming regions, and it sets the large-scale context for understanding any single star at its heart. As the narrative moves inward in later sections, each successive step will take place against this background of a young, crowded and energetic cluster, whose brightness anchors the core of the Tarantula Nebula in the outer reaches of the Large Magellanic Cloud. Deep in the crowded heart of R136, the high stellar density shapes almost every aspect of the cluster's behavior, from the way stars move to the way light and wind fill the surrounding space. In an ordinary part of a spiral galaxy like the region around the Sun stars sit far apart, separated by light years of mostly empty space, and close encounters between them are extremely rare. In R136, the situation is very different. Here, many thousands of stars share a volume only a few light years across, and the most massive and luminous members gather preferentially toward the center, creating a compact core where the sky would appear bright in almost every direction. Astronomers describe this tendency for heavy stars to sink toward the middle as mass segregation, a natural outcome of many small gravitational interactions that slowly rearrange the cluster's contents over time. In such an environment, every star feels not just the pull of the cluster as a whole, but also the tugs from many neighbours, and the combined effect produces a pattern of motions that can be described statistically rather than by tracking each orbit in detail. Observers speak of the velocity dispersion of the cluster, a measure of how fast stars move in different directions relative to one another. In R136, this dispersion reaches tens of kilometers per second, fast enough that a star could cross the central region in a time that is short compared with its total lifespan. These motions are still slow by the standards of light, yet they are rapid on the scale of a young cluster, and they show that R136 is a strongly gravitationally bound system whose stars are held together by their mutual attraction despite their high speeds. The brightest stars in R136 stand out in this moving crowd as blue-white points whose light dominates the cluster's total luminosity. Many of them are of spectral types associated with the highest masses with surface temperatures of tens of thousands of degrees Celsius and luminosities that can reach millions of times that of the Sun. A relatively small number of such massive stars contribute a large fraction of the cluster's total light and wind power, while the far more numerous low-mass stars add mass but less radiation. This uneven distribution means that the bright stars act as local beacons and engines carving channels in the surrounding gas with their winds and ionizing vast regions with their ultraviolet radiation. Some of these luminous members are arranged in tight groupings in the very core of the cluster, coming so close together on the sky that early observations could not separate them. Only with the sharp vision of space-based telescopes and advanced techniques on large ground-based telescopes have astronomers been able to distinguish individual stars in the densest regions and assign spectra and brightness values to each. The overall gravitational potential of R136 can be estimated from the motions of its stars. By measuring how fast stars move and how their velocities are distributed, researchers infer the total mass needed to keep the cluster bound. These studies suggest that R136 contains several 100,000 solar masses of stars, making it one of the most massive young clusters known in the local universe. Within this total, the central parsec holds an especially large share of both mass and luminosity, with a smooth rise in stellar density toward the center. If an observer could drift through this core, the view would show a layered structure of brightness, with a relatively gentle fall-off in the number of bright stars toward the outer parts, and a crowded, almost continuous glow in the very middle. The motions within the cluster are not purely random. Some stars move on orbits that take them in and out of the core, while others are more tightly bound to the central region. Close gravitational encounters between stars, especially in the densest areas, can alter their paths, change their speeds, or in extreme cases eject them from the cluster entirely as runaway stars. Over many millions of years, such encounters may gradually reshape the cluster, spreading some stars outward while allowing the core to contract and grow denser. At the present very young age of R136, this long-term evolution has only begun, but the early signs of mass segregation and the high-velocity dispersion already hint at the dynamical processes at work. The cluster is also rich in binary and multiple star systems where two or more stars orbit a common center of mass. In a dense environment, these systems play a special role in the dynamics, because interactions between binaries and single stars or between two binaries can exchange energy and angular momentum. Hard binaries in which the stars orbit closely can act as energy sources for the cluster when encounters tighten their orbits and give kinetic energy to passing stars. This quiet, ongoing trade of energy helps support the cluster against collapse and contributes to the gradual expansion of its outer parts. At the same time, the presence of many binaries among the most massive stars has implications for how those stars formed and how they may later evolve. The bright stars that populate the upper end of the cluster's mass distribution do not sit fixed in space. They travel on orbits within the shared gravitational field, and their paths may bring them close to one another, changing their winds and radiation fields in subtle ways. Colliding stellar winds can produce hot shocked gas that emits X-rays, adding another layer of emission to the already complex radiation environment. Observations of X-ray emission from the Tarantula Nebula region show a diffuse glow as well as point sources, some of which are associated with massive stars and their wind interactions. Within the dense core of R136, where separation between the brightest stars is only a fraction of a light year, such interactions likely contribute to the high energy output of the region. Yet despite this complexity, the cluster maintains a kind of statistical order. The motions of stars when averaged over many objects follow patterns consistent with a system in approximate virial balance, where the kinetic energy of stellar motions and the potential energy of gravity are related in a way that keeps the cluster bound but not collapsing rapidly. This balance is not exact or static, especially in so young a cluster, but it provides a useful framework for understanding the present state of R136. All of these features together define the dynamic character of the cluster. It is not only a static snapshot of many bright stars packed into a small space, but a living system in which stars move, interact, and share energy on timescales that are short compared with the history of the host galaxy. The extreme density and high luminosity of its central region create the conditions under which some of the most massive stars can form and exist. Among these, certain objects stand out as especially luminous, including R136a1, which sits as one of the most radiant members of the core. In this way, the dense bright cluster provides the gravitational and radiative setting for the most massive stars known to observation, and the motions and light of all its members together define the environment in which they live. The combined energy output of R136 floods the surrounding Tarantula Nebula with light and wind, turning the local region into one of the most luminous star-forming complexes in the nearby universe. The cluster's very hot, massive stars emit most of their light at short wavelengths, especially in the ultraviolet, and this radiation pours outward in all directions, striking the clouds of hydrogen and other gases that still linger nearby. When ultraviolet photons meet neutral hydrogen atoms, they can remove electrons from them, ionizing the gas and creating large regions where hydrogen exists as a plasma of protons and free electrons. These ionized zones, often called H2 regions in astronomy, surround young hot stars and glow with a characteristic reddish light. When electrons recombine with protons and fall back to lower energy states. In the Tarantula Nebula, the cluster's ionizing radiation powers an enormous H2 region, lighting up a volume that spans many tens of light years and making it visible as a bright, intricate structure even from the far distance of the Milky Way. Within this glowing volume, the gas is not arranged in a smooth sphere. Instead, the radiation and winds from R136 carve out cavities, compress shells, and pick out dense filaments in a constantly changing pattern. Where the radiation meets dense clumps of gas, it can erode the exposed surfaces, creating sharp edges and pillar-like forms that point back toward the cluster. Shadows form behind these dense knots where the ionizing light cannot reach, and there the gas can remain relatively cool and neutral. Observations of the Tarantula Nebula at different wavelengths show a rich tapestry of such structures, with bright ridges of ionized gas outlining the boundaries between hot low-density cavities and cooler, denser clouds. The brightness of the nebula reflects not only the high intrinsic luminosity of R136, but also the geometry and density of the gas that receives this energy. In regions where the gas is thick, the ionization front can move more slowly, and the nebula appears as sharply defined arcs and rims. In more diffuse areas, the ionized zone can extend farther from the cluster, creating a softer, more extended glow. The radiation does not simply light the gas, it also exerts pressure on it. Each photon carries momentum, and when large numbers of photons are absorbed or scattered by dust grains and gas, they can push the material outward. This radiation pressure, combined with the mechanical force of stellar winds, sweeps gas away from the central parts of the nebula, gradually clearing a cavity around the cluster. Within this cavity, the gas density drops, and the hot shocked winds from massive stars can fill the space with a low-density plasma at temperatures of millions of degrees Celsius. Such hot gas emits X-rays, and observations with X-ray observatories do indeed show a diffuse high-energy glow in parts of the Tarantula region, consistent with a mixture of stellar wind shocks and possibly some contributions from early supernova remnants elsewhere in the complex. The stellar winds themselves are streams of charged particles, mainly protons, electrons, and some heavier ions, driven off the surfaces of hot stars by radiation pressure acting on ions in their outer layers. In R136, many massive stars launch winds at speeds of thousands of kilometers per second. When these winds collide with the surrounding medium, including the winds of neighboring stars, they create shock fronts that heat the gas and structure the nebula. Over time, the kinetic energy carried by the winds is converted into thermal energy of the gas and mechanical work against the surrounding clouds, contributing significantly to the overall feedback that R136 exerts on its environment. This feedback can both hinder and promote further star formation. In the central cavity where gas is swept away, conditions become less favourable for new stars to form, since the raw material is dispersed and heated. Along the edges of the expanding bubble, however, gas may be compressed as the pressure from inside pushes against denser clouds outside. Compressed gas can cool and fragment, sometimes forming new dense cores that may collapse under their own gravity to form stars. Thus, the same forces that clear the inner region can trigger new star formation farther out, creating a layered pattern of stellar ages and compositions around the cluster. In the Tarantula, nebula observations reveal many smaller clusters and associations spread around the main complex, some of which may be related to this kind of triggered activity. The overall ionization structure of the nebula, including its bright arcs and less luminous interior, can be modeled by radiative transfer calculations that take into account the positions and luminosities of the massive stars in R136 and the distribution of gas and dust. These models aim to reproduce the observed emission line strengths and surface brightness patterns by tracking how photons move through the gas and where they are absorbed. In general, such models show that a relatively small number of very luminous stars dominate the ionizing budget, while the many less massive stars contribute more modestly. This concentration of ionizing power means that changes in the evolution of a few key stars, such as their gradual cooling or increased mass loss, can alter the nebular emission over time. For now, with the cluster still extremely young, the ionization remains intense, and the Tarantula Nebula shines as one of the brightest star-forming regions known in the local group of galaxies. The gas and dust do not respond only to radiation and wind. They also reflect and scatter starlight. Dust grains mixed with the gas scatter blue light more efficiently than red, creating subtle color gradients in scattered light that overlay the emission from ionized gas. Infrared observations reveal warm dust that has absorbed ultraviolet and visible photons and re-radiates this energy at longer wavelengths, giving another view of how the cluster's power is distributed. Together, these different bands show a complex interplay of emission, scattering, and absorption, all driven at root by the high luminosity of R136. The total energy output of the cluster can be compared with that of an entire small galaxy. When all the stars in R136 are considered together, their combined luminosity reaches many millions of times that of the Sun. This enormous power output is concentrated into a small volume, so the radiation field near the cluster is extremely intense. Gas clouds located close to the core experience far higher fluxes of ultraviolet light than typical clouds elsewhere in the Large Magellanic Cloud, and their physical state reflects this. They are more highly ionized, hotter and more turbulent, with a mixture of photoionization, heating, and mechanical stirring by winds. Spectroscopic observations of emission lines from the Tarantula Nebula provide direct evidence of these conditions, showing temperature-sensitive line ratios and broadening that match models of gas influenced by strong stellar feedback. Over longer timescales, the continuous input of energy from R136 may help to disrupt the parent molecular cloud that originally gave birth to the cluster. As gas is ionized and swept away, the reservoir of cold, dense material available for future star formation declines, eventually bringing the most active phases of star birth in this region to an end. In this sense, the cluster accelerates its own isolation, creating a relatively gas-poor cavity around itself, while enriching the wider region with heavier elements carried outward by winds, and later in its history by supernova explosions of massive stars. At the present stage, however, the system appears as a vivid snapshot of a young cluster still deeply coupled to its parental nebula, with radiation, winds and gas locked in a continuous exchange. This exchange defines the appearance of the Tarantula Nebula seen from afar and sets the physical context for any individual star within R136. The intense energy field produced by the cluster as a whole shapes the temperature ionization state and structure of the nearby gas, and it is within this bright sculpted environment that the most massive stars carry out their short luminous lives. At the very center of R136, the smooth impression of a single bright knot resolves under high magnification into a tightly packed group of the most luminous stars in the cluster, and among them lies the object known as R136a1. In early ground-based images, this region appears as a blurred core where individual points of light merge into one another. But space-based telescopes and advanced adaptive optics on large mirrors reveal that the core is in fact a compact multiple system made up of several extraordinarily bright stars separated by small fractions of a light year. The angular distances between these stars on the sky are tiny, so that even with the sharpest instruments it takes careful analysis to distinguish their individual contributions to the combined light. Astronomers assign labels such as R136a1, R136a, and others to these central members not to suggest that they are a single object, but to keep track of the multiple components that together define the very core of the cluster. Each of these stars ranks among the most luminous known, and the fact that several such objects reside so close together is one of the striking features of this region. The central grouping is embedded in a wider cloud of massive stars that also shine intensely, but the innermost few appear to shoulder a disproportionate share of the cluster's radiative output. Spectroscopic observations, which record how the intensity of light varies with wavelength, show that the core stars have spectra characteristic of very hot hydrogen, rich luminous stars with powerful winds, similar in some respects to classical Wolf-Rayet stars but still in a phase where hydrogen burning continues in their cores. Their emission lines are broad a sign that the gas in their winds moves at high speeds, and their continua are very bright at ultraviolet and blue wavelengths, indicating surface temperatures of tens of thousands of degrees Celsius. When models are fit to these spectra, taking into account the effects of distance, interstellar dust and wind opacity, they suggest that the luminosities of the core stars reach millions of times that of the Sun. R136a1 in particular emerges from such analyses as one of the brightest. The exact value of its luminosity and mass depends on the details of the models and the quality of the data, and these estimates have been refined over time as better observations and more sophisticated atmosphere codes become available. Earlier studies which treated the core as more blended suggested that R136a1 might possess a mass of order, a few hundred solar masses, perhaps close to 200 or even more. Later work that more carefully disentangles the contributions of neighbouring stars and uses updated models tends to favour somewhat lower masses, closer to around 100 to 150 solar masses, although the uncertainties remain significant. What remains robust is that R136a1 is an extremely massive and luminous star standing near or at the top of the observed mass range in the cluster. Its neighbours in the core, while slightly less extreme, are themselves very massive, and together they form a compact association in which the distances between stars are small enough that their radiation fields and winds overlap. In such a setting, no star can be considered in isolation. The ultraviolet photons from each core star contribute to a shared radiation field that bathes the others, and their winds collide in a network of shock fronts where gas is heated to high temperatures. This network is not directly imaged in fine detail because the scales involved are smaller than the resolution of current telescopes at most wavelengths, but its presence is inferred from the combined spectral signatures and from high-energy emission detected from the region. The gravitational fields of the core stars also interact. Although the overall gravitational pull of the cluster dominates on large scales in the immediate surroundings of R136a1 and its companions, the local potential is shaped by their individual masses. It is likely that several of them form binary or multiple systems, where two or more stars orbit one another in relatively tight configurations. Evidence for such multiplicity comes from subtle changes in spectral line profiles over time and from the difficulty of explaining their luminosities and spectra with single-star models alone. Close binaries can exchange mass, alter their evolution, and generate especially strong wind collision zones, all of which add layers of complexity to the physical picture of the core. Directly resolving these orbits is challenging because of the great distance to the cluster and the small angular separations involved. So much of the information about multiplicity comes from indirect methods and remains under active investigation. The spatial distribution of the most massive core stars is not random. They are concentrated within a tiny central volume whose radius is less than a light-year a scale, that is small compared with the overall size of the cluster, yet still large compared with their individual diameters. This compactness means that if an observer were located near R136a1, the nearby sky would be crowded with other enormous stars shining almost as brightly separated by angles many times larger than the apparent diameter of a full moon, but still small on astronomical scales. The local radiation field would be dominated not by a single source, but by the combined output of several, and the surrounding gas would experience a nearly continuous barrage of ionizing photons from all directions. The winds from the core stars would flow outward, collide and merge into a complex pattern of high-speed streams, shocks and turbulent eddies, creating a very dynamic environment on scales comparable to the distances between the stars. Within this environment, R136a1 marks a kind of peak in the distribution of stellar properties, representing the extreme end of mass and luminosity that nature has produced in this cluster. Its position among other very massive stars raises questions about how such an object formed. Did it assemble its mass directly from the collapse of a single very massive gas core, or did it grow through mergers of smaller protostars in the crowded center of the young cluster? Present observations do not yet provide a definitive answer, and models of massive star formation under such extreme conditions remain an area of active work. What can be said is that the central concentration of mass in R136, together with the evidence for dynamical interactions and high stellar densities, make it plausible that processes beyond simple isolated core collapse have played a role. In the present narrative, however, the focus stays on describing the current configuration of the core rather than its detailed history. The central region appears as a tight assembly of very luminous stars, with R136a1 as one of the most prominent members, embedded in the diffuse glow of fainter, massive companions and the residual nebula light that pervades the cluster. The scene is one of continuous brilliance with no true darkness between the stars, and it is against this backdrop that closer attention will later turn to the immediate gaseous and radiative environment around R136a1 itself. For now, the emphasis remains on understanding that this star does not stand alone but shares a small and intensely lit neighborhood with other giants in the heart of R136, each contributing to the extraordinary conditions that prevail in the cluster's core. Around R136a1, the gas and radiation form a small but intense world of their own, nested inside the larger cavity carved by the whole cluster. The star sits within a bubble of ionized gas where its light and wind dominate the local conditions, even though the combined radiation of the neighboring massive stars remains strong. In this immediate environment, ultraviolet photons streaming from R136a1 strike any remaining neutral hydrogen, and helium ionizing them and maintaining a zone of hot plasma where the gas is kept at temperatures of many thousands of degrees Celsius. The density in this bubble is relatively low because stellar winds and radiation pressure have swept much of the original material away, but the pressure is high, set by the combination of thermal motion of particles and the continuous input of energy from the star. The boundary of this bubble is not a sharp sphere. Instead, it is shaped by the distribution of gas and by the presence of other winds and radiation fields nearby. In directions where the surrounding gas is denser, the expansion slows and bright rims or arcs may form as the ionization front and wind-driven shocks compress the material. In directions where the gas is more diffuse, the bubble can extend farther, merging smoothly into the wider cavity, cleared by the core of 136. Within this volume, the light field is extremely intense. An atom or dust grain does not experience radiation from R136a1 alone, but from the entire core. Yet at very small distances from the star, its contribution is particularly strong. Photons emerge from the outer layers of the star and travel only a short distance before they meet gas dust or electrons in the wind. Some are absorbed outright, heating the gas. Others scatter off free electrons in a process that redistributes their directions without greatly changing their energies. The result is a radiative environment in which energy flows outward, but is constantly redirected and diffused, creating a soft yet overwhelmingly bright field in all directions. Dust grains that survive in this region are heated to high temperatures and re-radiate the absorbed energy at infrared wavelengths. But close to the star, many grains are destroyed, leaving a plasma dominated by ions and electrons. The stellar wind of R136a1 fills this bubble with matter streaming outward at high speed. Line-driven winds from such hot, massive stars can reach velocities of thousands of kilometers per second, and the material they carry away interacts with both the ambient gas and the winds from neighboring stars. The wind begins in the star's extended outer atmosphere, where radiation pressure acts on ions and gradually accelerates the gas outward. At small radii, the flow is dense and still being pushed to higher speeds. Farther out, it becomes more rarefied but maintains a large momentum. When this wind meets the surrounding medium, it slows abruptly in a shock front, converting kinetic energy into heat and raising the temperature of the post-shock gas to values high enough to emit X-rays. Where winds from different stars collide, a network of such shocks can form with complex geometries that change as the stars move on their orbits and as instabilities develop in the flowing gas. The immediate environment of R136a1 is therefore likely threaded by thin layers and sheets of shocked gas separated by regions of lower density where the wind streams more freely. Observationally, this environment is sampled through emission lines and continuum radiation at multiple wavelengths. In the optical and ultraviolet broad emission features in the spectrum of R136a1, trace the conditions in its wind-revealing velocities, densities, and ionization states. In X-rays, the combined emission from wind collision zones in the core of R136 appears as both point-like and diffuse sources, though current instruments cannot easily separate the contribution from R136a1 itself from that of its neighbours. Infrared observations detect warm dust and gas in the surrounding nebula, showing where the intense radiation has heated nearby material. By combining these data, astronomers reconstruct a picture in which the star resides in a high-pressure, high-radiation bubble, bounded by interfaces where its wind and light meet those of other stars and the remaining gas of the Tarantula Nebula. The gas inside this bubble is not static. It flows outward with the wind cools as it expands and is continually replenished by material leaving the star's outer layers. The mass loss rate, a measure of how much mass the star sheds over time, is inferred from spectral diagnostics that depend on wind density and geometry. For R136a1, these diagnostics indicate a very strong wind, capable of removing a significant fraction of the star's mass over the relatively short span of its life. As mass flows into the wind, it carries with it elements processed in the stellar interior and brought to the surface by mixing such as helium and nitrogen-enriched material. Over time, this enriches the surrounding gas with heavier elements, altering its cooling properties and the chemistry of any future generations of stars that might form from it. The local radiation field also influences the microphysics of the gas. Strong ionizing fluxes keep many atoms in high ionization states, reducing the efficiency of cooling through certain emission lines and maintaining higher temperatures than would be the case in a weaker field. The balance between heating by radiation and cooling by line emission and expansion determines the thermal structure of the bubble, while the balance between wind pressure, gas pressure, and the pressure of the surrounding medium determines its size and shape. Magnetic fields threaded through the gas and possibly carried outward by the wind add another component to this balance, though their detailed structure in this region is not yet well constrained by observations. Taken together, these factors create a layered environment in which conditions change smoothly with distance from the star. Close in, the wind is dense and rapidly accelerating. Farther out, it is thinner and interacts strongly with other flows. At the edge, it meets the ambient medium in shocks that define the outer boundary of the immediate bubble. Superimposed on this structure are gradients in radiation, intensity, ionization state, and temperature. All of this exists within the broader context of the cluster core, where overlapping bubbles from other massive stars and the global cavity carved into the Tarantula Nebula combine to form a multi-scale feedback structure. Yet on the scale of a fraction of a light-year around R136a1, the star's own wind and light remain the primary sculpting agents. In this way, the local environment of R136a1 can be viewed as a small, intense laboratory for the interaction between radiation stellar winds and interstellar gas, under extreme conditions governed by the star's exceptional luminosity and mass, but also shaped by its equally luminous neighbours. The details of this environment set the outer boundary conditions for the star's observable atmosphere and help determine how its energy and processed material are communicated to the surrounding nebula. The outer atmosphere of R136a1 forms the visible and measurable interface between the star's deep interior and the surrounding wind-filled bubble, and in a very massive hot star like this, the distinction between atmosphere and wind becomes blurred. In ordinary stars with weaker outflows, the atmosphere can be thought of as a relatively thin shell where light last interacts with matter before escaping into space, and the wind is a more tenuous flow that carries gas away from the surface. In R136a1, the wind is so dense and the radiation so strong that the region where light decouples from matter is extended and resides partly within the outflow itself. Astronomers describe such stars as having a pseudo-photosphere, a layer in the wind where the optical depth drops to a level that allows photons to escape freely, even though the gas there is already in motion rather than at rest. This extended atmosphere gives R136a1 the spectral appearance of a Wolf-Rayet-type star with broad emission lines formed in the accelerating wind and with only weak or absent absorption features that would normally arise in a static photosphere. A stellar atmosphere in this context is a stratified region where temperature, density and velocity change with distance from the center. Close to the underlying hydrostatic layers where gas is still approximately in balance, under the competing forces of gravity and pressure, the density is high and the temperature is set by the energy flowing outward from the interior. In R136a1, this energy flux is extremely large because the star's luminosity reaches millions of times that of the Sun. As radiation moves outward, it interacts with ions in the gas, especially metal ions such as iron, carbon, nitrogen and oxygen, whose spectral lines provide many channels for absorbing photons. When these ions absorb photons, they gain momentum, and in a very luminous star, the cumulative effect of this absorption can overcome gravity and push the gas outward, launching a line-driven wind. In the outer layers of R136a1, this process operates over a wide range of radii so that gas is steadily accelerated from subsonic to supersonic speeds as it flows away from the star. The structure of the wind and atmosphere is often described by models that solve the equations of radiative transfer and hydrodynamics simultaneously, since the radiation field and the gas flow are tightly coupled. These models show that the density decreases with radius, while the velocity increases from near zero at the base of the wind to thousands of kilometers per second at large distances. The temperature profile is more complex with high values in the deep layers, a drop in regions where the gas expands and cools, and reheating in shocked zones where instabilities or collisions between different wind streams occur. Because the wind is optically thick in many spectral lines, and even in the continuum at some wavelengths, the emergent spectrum is shaped by emission and scattering throughout this extended structure, rather than by a single sharp surface. Spectra of R136a1 display strong, broad emission lines of helium and nitrogen, among other elements formed in the dense inner wind where recombination and scattering processes are efficient. The widths of these lines indicate high terminal wind speeds, while their strengths and profiles encode information about density ionization and clumping in the outflow. Clumping refers to the presence of small-scale density variations, where the gas is not smoothly distributed but concentrated into knots and filaments. Line-driven winds are naturally prone to such instabilities, and models suggest that the wind of a very luminous star like R136a1 is likely structured in this way. Clumping affects the interpretation of mass loss rates, because emission processes often scale with the square of density, so models that assume a smooth wind can overestimate the amount of mass being lost. Modern analyses therefore include parameterizations of clumping to better match the observed spectra. The outer atmosphere also sets the radiative properties that determine how the star appears in different bands of the electromagnetic spectrum. The effective temperature, a quantity that characterizes the overall color of the star, is defined in terms of the total luminosity and the radius of the layer from which most of the radiation escapes. In a star with an extended optically thick wind, this radius is larger than the radius of the underlying hydrostatic core, and the effective temperature can be lower than the temperature of deeper layers, even though the star remains extremely hot by ordinary standards. For R136a1, effective temperatures derived from atmosphere models fall in the range of many tens of thousands of degrees Celsius, placing it firmly in the class of very hot stars. The combination of high effective temperature and large radius yields the enormous luminosity inferred for the star. Radiation pressure in the atmosphere plays a central role in maintaining this structure. In massive stars, the outward push of radiation on electrons and ions partially counteracts gravity even in static layers, and there exists a theoretical luminosity above which radiation pressure would exactly balance gravity in a fully ionized gas. R136a1 is thought to approach this limit closely. In the outer atmosphere, where line opacity adds extra channels for momentum transfer, the effective radiative force can exceed gravity in some regions driving the wind. The proximity of the star's luminosity to this balance point means that small changes in composition temperature or density can significantly alter the strength of the wind and the structure of the atmosphere. This sensitivity is one reason why precise modelling of R136a1's outer layers is challenging, and why different analyses can yield somewhat different mass and mass loss estimates. The chemical composition of the atmosphere carries signatures of internal mixing. Observations show enhanced helium and nitrogen in the winds of very massive stars in R136, including R136a1, compared with levels expected from the initial composition of the Large Magellanic Cloud. This suggests that material processed by hydrogen fusion through the carbon-nitrogen-oxygen cycle has been transported from deeper layers to the surface. Such mixing can be driven by rotation, convection, or other instabilities in the interior, and its presence in the atmosphere affects both the opacity and the wind driving, since different elements contribute differently to line acceleration. At the same time, the abundance patterns provide clues to the internal structure and evolutionary state of the star, though interpreting them requires coupling atmosphere models to stellar evolution calculations. From the perspective of the surrounding nebula, the outer atmosphere and wind form the immediate source of both ionizing photons and mechanical energy. Photons that escape from the pseudo-photosphere travel into the local bubble described earlier, where they ionize gas and heat dust. The wind carries mass and momentum outward, feeding the high-pressure cavity that surrounds the star. The rate at which mass leaves the atmosphere, the velocity it attains, and the composition of the outflow all determine how R136a1 contributes to the chemical and dynamical evolution of the Tarantula Nebula. Over the brief main sequence life of such a star, the outer layers may shed many solar masses of material, replacing a significant fraction of the original envelope with gas that has been processed by nuclear reactions in the interior. All of these properties are inferred from observations that probe only the light emerging from the extended atmosphere. No direct image resolves the surface of R136a1 itself, because the star is far away, and its apparent size is far below the resolution of current telescopes. Instead, astronomers rely on atmosphere models that adjust temperature, density, velocity, and composition profiles until synthetic spectra match the observed one across many wavelengths. The success of such models in reproducing line strengths and profiles provides confidence in the broad picture of a very hot luminous star with a dense line-driven wind and an extended pseudo-photosphere. At the same time, discrepancies between models and data point to complexities such as clumping, multidimensional structure, and perhaps magnetic fields, whose detailed roles remain areas of ongoing research. In the present view, the outer atmosphere of R136a1 appears as an active, continuously flowing layer rather than a static shell in which radiation and matter are closely coupled. It is the region where energy from the interior is finally converted into escaping light and into the kinetic energy of the wind, and it marks the boundary between the stellar body and the surrounding cluster environment. Understanding this outer wind and atmosphere is essential for interpreting the star's luminosity, effective temperature, and mass loss, and it sets the stage for considering the inner layers beneath where nuclear fusion and internal structure control the star's deeper behavior. Just beneath the extended wind and pseudo-photosphere of R136a1 lies a region where the gas gradually moves from a freely flowing outflow to layers that are close to hydrostatic balance, and in this transitional zone the near-surface structure of the star is set. In ordinary language, this is the place where the bright visible part of the star has its physical roots, where radiation, gas pressure, and gravity all act together to determine how light emerges and how the outer layers respond. Although no telescope can resolve these layers directly, their presence is felt through the way the emergent spectrum looks, and through the inferred properties of the wind. The concept of a photosphere, the layer from which most of the star's light escapes, must be adjusted in a star with such a powerful optically thick wind. Instead of a thin, sharply defined surface, the photosphere of R136a1 is more like a fuzzy zone that stretches across a range of radii, with deeper parts still nearly static and upper parts already being accelerated outward by radiation pressure. In these depths, the gas is still dense, and the mean free path of a photon is very short, so radiation moves outward only by many successive scatterings and absorptions. The temperature remains extremely high, at tens of thousands of degrees Celsius and above, so that hydrogen and helium are highly ionized, and heavier elements are stripped of many of their electrons. Opacity. The degree to which the gas resists the passage of radiation comes from several sources here, including scattering by free electrons and absorption in countless spectral lines of metal ions. The balance between opacity and the energy flux from below determines how steeply the temperature falls with radius, and how quickly the gas can radiate away the energy carried upward from the fusion-powered core. In very massive stars like R136a1, the luminosity is so large that the outward push of radiation on electrons nearly cancels the inward pull of gravity in parts of the near-surface layers. This condition is sometimes described in terms of a limiting luminosity at which radiation pressure would exactly balance gravity in a simple gas. R136a1 appears to approach this limit in its outer envelopes, meaning that the gas there is held in a delicate balance. Slight changes in local opacity, perhaps due to variations in temperature or composition, can tip this balance, leading to zones where the effective gravity is reduced and the gas becomes more easily accelerated outward. In this way, the near-surface layers form the launching region of the wind, where material is lifted out of hydrostatic support and begins its journey into the extended atmosphere described earlier. The structure of these layers is influenced by both radiative and convective energy transport. In many stars, including the Sun, convection, a process in which hot gas rises and cooler gas sinks, plays an important role in carrying energy through certain regions. In very massive hot stars, the central parts are often strongly convective, while the outer layers are mainly radiative. However, there is evidence from models that even in the envelopes of such stars, local convective zones can appear, where opacity increases suddenly with temperature, such as in layers where iron or other heavy elements contribute many spectral lines. In R136a1, these so-called opacity bumps may create thin convective zones near the surface, where rising and sinking motions stir the gas and mix chemical elements. Although these convective layers are not directly observed, their existence is suggested by theoretical calculations and may help explain the surface abundance patterns seen in the spectra. Mixing in the near-surface layers can bring helium and nitrogen-enriched material from deeper zones upward, while freshly accreted or less processed material may be carried down. This mixing affects not only the composition, but also the opacity, since different elements and ionization states absorb radiation in different ways. The near-surface zone is also where rotation exerts a strong influence. Very massive stars are believed to rotate at significant fractions of their breakup speeds, the speeds at which centrifugal forces would begin to overcome gravity at the equator. If R136a1 rotates rapidly, its surface will not be spherical in a strict sense, and the effective gravity will vary with latitude being lower at the equator than at the poles. This variation can lead to gravity darkening, where the equatorial regions with lower effective gravity are slightly cooler and darker than the poles, which are hotter and brighter. In such a case, the near-surface temperature and flux distribution are not uniform, and the wind may be stronger in some directions than others. Current observations do not resolve this anisotropy directly, but the general principles of rotating star structure suggest that it likely plays a role in how the near-surface layers of R136a1 behave. Magnetic fields, if present, could further channel the flow of gas, but their strength and geometry in this star are not well constrained, so any such effects remain uncertain. Small-scale inhomogeneities also arise naturally in the near-surface layers. The same line-driving instability that fragments the wind into clumps can originate close to the base of the outflow, as tiny perturbations in velocity or density grow under the action of radiation forces. As a result, the transition from static atmosphere to wind is probably not smooth and steady, but peppered with regions of slightly higher and lower density, which may leave subtle imprints on spectral line profiles. Turbulent motions, both from convection and from these instabilities, may broaden spectral features beyond what would be expected from thermal motions alone. In spectral modelling, this is often represented by a microturbulent velocity field, a parameter that stands in for unresolved small-scale motions in the gas. The near-surface layers are also the origin of continuum polarization in the star's light, if the geometry of the atmosphere and wind departs from perfect spherical symmetry. Scattering of photons by free electrons in an asymmetric envelope can imprint a weak polarization signal on the emergent light, and measurements of this polarization can give clues about the large-scale shape of the atmosphere and wind. In a perfectly spherical static star, such polarization would cancel out, but in a rotating wind-driven star like R136a1, small deviations from symmetry may produce detectable effects. Some very massive stars exhibit time-variable line profiles and light curves that suggest changes in their near-surface structures on timescales of days to weeks, possibly due to pulsations or evolving spots of different temperature or opacity. Whether R136a1 shows such behavior in detail is not yet fully established, but the theoretical possibility illustrates how sensitive the near-surface balance is to small disturbances. This sensitivity stems from the fact that radiation pressure and gas pressure are both important, and the system operates close to the threshold at which outward forces could overwhelm gravity. In the context of the star's overall life, the near-surface region acts as a regulatory layer that adjusts how energy and mass flow from the interior into the wind. If the mass loss rate increases, the structure of the outer layers can change, altering the radius and effective temperature. If mixing brings new elements to the surface, the opacity changes, and the coupling between radiation and matter adjusts. Stellar evolution models that aim to follow R136a1 through its brief but intense life must therefore link the physics of these near-surface layers to the deeper interior, since changes here can feed back on the star's internal stratification and vice versa. Yet from an observational point of view, the near-surface zone remains an inferred structure, deduced from the signatures it leaves on the emergent spectrum. By fitting atmosphere models that include a transition from hydrostatic layers to an accelerating wind, astronomers can constrain the temperature, density and velocity structure across this region, but the details are still approximate, and multiple model configurations can produce similar spectra. For this reason, the precise thickness and behavior of the near-surface layers in R136a1 are subjects of ongoing study, with different research groups exploring the role of rotation clumping and varying opacities. Despite these uncertainties, the broad picture is clear. Just below the extended flowing pseudo-photosphere lies a zone where the star's light, the pressure of its gas, and the pull of its gravity come into a close balance, moderated by mixing and possibly by rotation. It is in this region that material either remains part of the star held back by gravity and pressure support, or is lifted into the wind, becoming part of the outflow that shapes the surrounding bubble. This near-surface structure is thus both the final layer of the stellar body and the initial layer of the stellar wind, and it forms a crucial link between the invisible depths of the interior and the luminous, observable outer flow that has already been described in earlier sections. Within the wider narrative of R136a1, these layers mark the threshold between the inner engine of nuclear fusion and the outer arena of radiation and wind, a threshold that will be approached more closely as attention turns inwards to the star's deep interior in later discussion, while still remaining rooted in what observations and models can reliably support today. Deep inside R136a1, the structure of the star is set by the balance between gravity pulling matter inward and the pressure of hot gas and radiation pushing outward, with nuclear fusion in the core providing the ongoing source of energy that maintains this balance. In such an extreme object, the interior differs in important ways from that of lower mass stars, yet it still follows the same general physical principles. The star can be thought of as a series of nested layers, with conditions becoming hotter and denser toward the center. In the outer parts near the regions already described, the gas is hot and ionized, but not yet at the highest temperatures and densities needed for the most intense fusion reactions. Deeper in the central core, hydrogen is converted into helium by chains of nuclear reactions that release enormous amounts of energy. For a star as massive and hot as R136a1, the dominant route for hydrogen burning is the carbon-nitrogen-oxygen cycle, in which pre-existing carbon, nitrogen and oxygen nuclei act as catalysts that help fuse protons into helium while cycling through different isotopic forms. This cycle is extremely sensitive to temperature, so that a modest increase in core temperature leads to a very large increase in energy generation. As a result, the energy production in the core is strongly concentrated toward the center, where temperatures and densities reach their highest values. Models of very massive stars suggest that core temperatures in such objects can reach many tens of millions of degrees Celsius, with central densities high enough that matter is in a fully ionized plasma state. Under these conditions, electrons and nuclei move rapidly, and nuclear reactions proceed at rates sufficient to support the enormous luminosity observed at the surface. In R136a1, the energy produced in the core must travel outward through the interior before it can escape from the atmosphere as radiation, or be carried away in the wind. The way this energy is transported affects the internal structure. In many lower mass stars, part of the interior is radiative, where energy moves mainly by the random walk of photons, and part is convective, where rising and sinking gas carries heat. For a very massive star like R136a1, theoretical calculations indicate that most of the interior is convective, especially in the central regions where fusion occurs. In a convective core, hot gas rises from the deepest layers, cools slightly as it moves outward, and then sinks back again, repeatedly cycling material and carrying energy outward in the process. This vigorous mixing tends to maintain a relatively uniform composition throughout the core because fresh hydrogen is continually brought into the regions where fusion is active and helium-rich material is distributed more evenly. The presence of a large convective core has important consequences for the star's evolution, since it allows R136a1 to use a larger fraction of its total hydrogen supply before exhausting the fuel in the center. Above the convective core, there may be regions where energy transport becomes more radiative and where mixing is less efficient. Even in these layers, however, rotation and internal waves may create additional forms of mixing that blur the boundaries between strictly convective and radiative zones. If the star rotates rapidly, the centrifugal force alters the effective gravity inside, and this can drive large-scale circulations that move material along meridional paths from equator to pole and back. Such rotational mixing can bring nitrogen-enriched material from the core region into the envelope, and may help explain the enhanced surface abundances inferred from the spectrum. In this way, the interior of R136a1 is not strictly stratified into isolated shells, but exhibits some degree of chemical and thermal coupling between different layers. The pressure inside the star has two main components: gas pressure, arising from the thermal motion of particles, and radiation pressure, arising from the momentum carried by photons. In less massive stars, gas pressure usually dominates, but in very massive luminous stars, radiation pressure can become comparable to or greater than gas pressure in large parts of the interior. In R136a1, models suggest that radiation pressure plays a major role throughout much of the core and envelope. This means that the equation of state, which relates pressure, temperature, and density, is strongly influenced by the photon gas, and small changes in temperature can lead to significant changes in total pressure. The dominance of radiation pressure makes the star more susceptible to certain kinds of instabilities, because if the outer layers expand and cool slightly, the radiation pressure can drop, allowing gravity to pull matter inward again, and these radial or non-radial pulsations can in principle grow under the right conditions. Whether such instabilities are active in R136a1 to a degree that produces observable variability remains an open question, but the underlying physical possibility is part of the internal picture. The overall mass distribution inside the star determines how gravity varies with radius. At each radius, the inward gravitational pull of the mass contained within that sphere must be balanced by the outward pressure gradient. This balance is described by the equations of hydrostatic equilibrium. When nuclear fusion in the core produces more energy, the increased temperature raises the pressure and can cause the outer layers to expand until a new balance is reached. When the core gradually converts hydrogen to helium, the mean molecular weight of the gas increases, changing the density and pressure structure and requiring further adjustments. In this way, 136a1 continuously self-regulates, adjusting its internal profiles of temperature, density, and pressure to keep the inward pull and outward push in balance over long periods, compared with the timescale of light crossing or sound waves. The interior is also the site of the star's internal sound waves and gravity waves, which can propagate through different regions and transport energy and angular momentum. These waves are difficult to detect directly in such distant massive stars, but studies of stellar oscillations in other types of stars suggest that they can contribute to mixing and to the redistribution of rotation inside. In R136a1, the combination of strong convection rotation and waves likely leads to a complex internal flow pattern, even though the star as a whole maintains a smooth, nearly spherical appearance when seen from afar. The exact mass of R136a1 remains uncertain, so models of its interior span a range of values typically from around 100 to more than 150 times the mass of the Sun. Within this range, the core occupies a large fraction of the total mass, and radius reflecting the star's strongly centrally concentrated energy generation. The core mass and size determine how long the current phase of hydrogen burning can last, which in turn sets the timescale over which the star can maintain its present luminosity and structure. More massive models have higher core temperatures and luminosities, but shorter lifetimes because they burn their fuel more rapidly. Less massive models burn more slowly, but are also somewhat less luminous. In all cases, however, the timescale for the hydrogen burning phase is short in absolute terms, likely only a few million years compared with the billions of years available to lower mass stars. From the point of view of the Tarantula Nebula, this means that R136a1 and its peers are transient features present during only a brief window in the history of the cluster. From the internal perspective, though, the star is in a relatively stable main sequence phase, with hydrogen fusion in the core, providing a steady energy source that holds gravity in check. Astronomers cannot probe the interior of R136a1 directly, but they can construct models that must reproduce the observed luminosity, effective temperature, surface composition, and wind properties. By comparing these models with the data, they infer the likely internal profiles of temperature density and chemical composition. Different research groups may adopt different assumptions about rotation mixing and mass loss, leading to somewhat different internal structures and evolutionary paths. Despite these differences, a shared picture emerges of an enormous hot convective core, in which hydrogen is being fused to helium under conditions of high temperature and high radiation pressure, surrounded by layers in which energy flows outward, and material is gradually enriched and mixed. This picture is consistent with the star's extreme luminosity and with the spectral signatures of processed material in its wind. It also underlines that R136a1 is not static inside. Its core composition is slowly changing, helium is accumulating, and the star is progressing through its main sequence life, even though, to outside observers, it may appear unchanging over human timescales. Within the framework of this description, the focus remains on the broad internal structure that current models support, emphasizing the central role of the convective hydrogen-burning core and the way it supports the star's outer layers, without advancing into later evolutionary stages that lie beyond the present phase. In this way, the deep interior of R136a1 can be understood as a powerful but regulated engine, converting hydrogen into helium and radiating the released energy outward, while the outer regions respond by adjusting their structure and by shedding mass into the surrounding nebula. The question of how R136a1 remains stable despite its extreme luminosity leads naturally to the balance between inward gravity and outward pressure, a balance that is maintained only within certain limits. At every point inside the star, gravity pulls matter toward the center, while the high temperature gas and intense radiation push outward. In many stars, gas pressure dominates this outward push, but in very massive hot stars like R136a1, radiation pressure becomes a major and sometimes dominant contributor. Each photon carries momentum, and when enormous numbers of photons stream outward through the star's interior and envelope, their combined effect can partly counteract gravity. Astronomers describe a theoretical threshold at which the outward force of radiation on fully ionized gas would exactly balance the inward pull of gravity. This threshold is called the Eddington limit. For a given mass, there is a corresponding maximum luminosity at which this balance would occur in a simple model. R136a1, with its very high luminosity and large mass, is thought to lie relatively close to this limit, at least in some parts of its envelope, although the exact distance from it remains uncertain because both the mass and the detailed structure of the outer layers are not known with perfect precision. When radiation pressure approaches the level of gravity in the outer layers, the effective gravity, which is the net inward pull, after subtracting the radiative push, becomes small. In regions where this effective gravity is very low, the gas is more easily lifted outward, and the star can develop an inflated envelope in which the density is reduced and the radius is larger than it would otherwise be. In such a configuration, slight local increases in opacity, for example, due to changes in temperature that affect the ionization state of iron or other heavy elements, can increase the radiative force and push the gas outward more strongly. This feedback can create layers where the gas is marginally bound, hovering near the point where even a modest additional radiative push would set it flowing outward as part of the stellar wind. In this way, proximity to the Eddington limit naturally leads to strong mass loss, because any layer in which radiation pressure comes close to cancelling gravity is vulnerable to being driven away. Line-driven winds, such as those already described in the outer atmosphere, are one manifestation of this process. In the dense inner wind of R136a1, radiation acts on a forest of spectral lines, imparting momentum to ions, and accelerating the gas outward from the near-surface layers. The strength of this wind depends on the luminosity, the mass, and the composition of the star, as well as on the distribution of opacity with radius. For such a luminous object, the allowed range of mass loss rates consistent with stability is limited. If the wind is too weak, the outer layers may remain so close to the Eddington limit that small perturbations could lead to larger instabilities. If the wind is too strong, the star would shed mass at a rate that would quickly alter its structure and perhaps move it away from the observed luminosity and temperature. Current atmosphere and wind models for R136a1 attempt to find solutions in which the radiation field, the density structure, and the outflow rate together satisfy the conditions of hydrostatic balance in the deeper layers and steady acceleration in the wind. These models indicate that the star loses mass at a very high rate compared with less luminous stars, but the exact value remains uncertain because it depends on details of clumping ionization and the assumed geometry of the wind. As mass is lost, the ratio of luminosity to mass changes, and this ratio is central to the question of how close the star is to the Eddington limit. For a given luminosity, reducing the mass brings the star closer to the point where radiation pressure would fully balance gravity. At the same time, changes in mass and composition affect the core structure and may alter the luminosity itself. Some theoretical studies suggest that very massive stars can regulate themselves through mass loss. If they become too luminous for their mass, stronger winds carry away material and reduce the mass until the ratio of luminosity to mass returns toward a more stable value. In this picture, stars like R136a1 may spend much of their lives operating near the edge of stability, but not crossing it in a catastrophic way. Instead, they adjust gradually, shedding mass and reshaping their envelopes while maintaining hydrostatic equilibrium in their interiors. How close R136a1 comes to any global instability is still a matter of investigation. Some very luminous stars in other environments show episodes of enhanced mass loss and brightness variations that mark them as luminous blue variables, objects thought to experience phases where their envelopes become unstable. For R136a1, the available observations so far do not show clear evidence for such large eruptive events, though the timescale over which the star has been monitored is short compared with its total lifespan. Any subtle variability due to pulsations waves or changes in the outer layers would be difficult to detect at the distance of the Large Magellanic Cloud, especially in the crowded core of R136, where light from many neighbours overlaps. As a result, the stability of R136a1 is inferred mainly from the success of steady atmosphere and wind models in reproducing its spectrum and luminosity, and from the absence of dramatic changes in the available data, rather than from detailed time-resolved studies of its brightness or line profiles. Within the interior, the dominance of radiation pressure in much of the core and envelope also raises the possibility of internal instabilities. When radiation pressure constitutes a large fraction of the total pressure, the response of the star to perturbations can differ from that of a gas pressure-dominated star. Small compressions or expansions in a radiation pressure-dominated region can produce changes in temperature and luminosity that either damp or amplify the disturbance. Detailed calculations explore whether such conditions can lead to radial or non-radial pulsations of significant amplitude. If present, these pulsations could modulate the near-surface structure, alter the wind launching conditions, and contribute to time-dependent mass loss. For R136a1 models must satisfy the constraint that any such oscillations do not produce variations in the energy output that conflict with the relatively steady appearance of the star in current observations. This requirement further narrows the range of structures and parameters that are considered plausible. The concept of an upper mass limit for stars is closely tied to these stability considerations. If a star above a certain mass cannot find a configuration in which gravity and radiation pressure balance without leading to runaway mass loss or severe instabilities, then such a mass may not be sustainable in practice. 136a1, being one of the most massive stars known, plays a central role in testing these ideas. If its mass lies nearer the higher end of current estimates, the star would sit closer to the region of parameter space, where theory predicts difficulties in maintaining stability. If the mass is lower, then the tension between observations and theoretical limits is reduced. In both cases, the presence of such a luminous star indicates that nature can assemble objects that operate in a regime where radiation pressure and gravity are finely balanced. The observed strong wind suggests that mass loss is already an important channel by which the star responds to this balance, carrying away material and limiting how far the luminosity to mass ratio can rise. Over the course of its hydrogen-burning phase, the total mass shed by R136a1 through its steady wind is expected, according to models, to amount to a substantial fraction of its initial mass. Each parcel of gas that escapes reduces the gravitational binding of the remaining envelope, and each change in envelope mass and composition feeds back into the internal structure and fusion rates. In this slow, continuous exchange, the star adjusts its internal and surface conditions to keep the forces balanced. The fact that atmosphere and interior models can find self-consistent solutions for R136a1 in which hydrostatic equilibrium holds in the deep layers and the wind is driven steadily in the outer regions, supports the view that the star currently exists in a stable main sequence state, albeit one that lies close to theoretical luminosity boundaries. At the same time, the sensitivity of this balance to small changes in opacity, mass and composition underscores why the uncertainties in the star's exact mass and structure remain significant. Different assumptions about clumping, rotation and mixing can shift the inferred distance from the Eddington limit and the derived mass loss rates. In this sense, R136a1 serves as a stringent test case for models of very massive star stability, mass loss and radiation pressure. Within the scope of present understanding, it appears as a star that maintains its structure by operating near but not beyond the limits set by gravity and its own light, with a powerful wind acting as the channel through which excess energy and momentum are carried away into the surrounding nebula. In its present state, R136a1 appears as a very young, hydrogen-burning, extremely massive star still in the main sequence phase of its life, even though the conditions under which it exists are far more extreme than those in ordinary main sequence stars. The surrounding cluster R136 is only a few million years old at most, and the spectral properties of its brightest members, including R136a1, indicate that they are still fusing hydrogen into helium in their cores. This places R136a1 in an early evolutionary stage in which the central hydrogen reservoir remains substantial, the core is convective and vigorously mixing, and the overall luminosity is supported by steady nuclear burning. The star's present structure, with a large convective core, a radiation pressure-dominated envelope and a dense line-driven wind, reflects this youth. Hydrogen fusion in the core maintains high temperatures and pressures, and the resulting energy flows outward through the interior, supporting the star against gravity and powering the immense luminosity that emerges at the surface. Over time, however, the core composition slowly changes. As hydrogen nuclei fuse into helium, the fraction of helium in the core increases, raising the mean molecular weight of the gas. This change affects the density and pressure structure and leads to gradual adjustments in the core and envelope. In a convective core, such changes are spread throughout a region that occupies a large fraction of the star's mass, so the central helium enrichment grows steadily during the main sequence phase. Even while this transformation proceeds, the star can maintain a quasi-steady state, in which the rate of energy generation from fusion balances the rate at which energy is radiated away, with the internal profiles of temperature and density adjusting slowly. At the same time, R136a1 is losing mass through its powerful stellar wind. Each moment, gas from the outer layers is accelerated outward and carried away, reducing the total mass of the star, while leaving its luminosity initially almost unchanged. As mass decreases, the ratio of luminosity to mass shifts and the structure of the envelope responds. The outer layers may become less tightly bound, the effective gravity at the surface may decline, and the wind may adjust in strength. Over longer timescales, this continuous shedding of mass can remove a significant fraction of the star's original envelope, exposing layers that were once deeper inside. Because the wind carries away material that has been partially processed by nuclear burning and mixed upward, the composition of the remaining surface layers also evolves. Helium and nitrogen enrichments observed in the atmosphere already hint that internal products of fusion have reached the surface in the current stage. As more mass is lost, this enrichment is expected to become more pronounced, and the star may evolve toward a state where it appears as a more classical, hydrogen-poor Wolf-Rayet-type object, with strong helium and nitrogen lines and a composition dominated by nuclear-processed material. The path that R136a1 follows in the space of luminosity and effective temperature can be described in terms of theoretical evolutionary tracks. For a given initial mass and composition, stellar evolution codes compute how the star's radius surface temperature, luminosity and internal structure change as hydrogen is consumed in the core and as mass loss peels away the outer layers. For very massive stars, these tracks show that the luminosity remains high and changes relatively slowly during much of the core hydrogen burning phase, while the effective temperature and radius may evolve more noticeably. In some models, the star begins its life extremely compact and hot, then expands somewhat and cools at the surface as the core processes hydrogen and the envelope responds. In others, rotation, mixing, and mass loss combine to keep the star relatively hot and compact throughout the main sequence. The details depend on assumptions about how efficiently mixing redistributes elements, how rapidly the star rotates, and how strong its wind is at each stage. What is common to these scenarios is that the core gradually becomes more helium-rich, and the overall mass decreases with time. For R136a1, the precise initial mass rotation rate and mixing efficiency are not directly observed. So models explore a range of possibilities that are consistent with the current luminosity spectrum and inferred mass. Some scenarios posit an initial mass significantly larger than the present mass, with the star already having shed tens of solar masses through winds even in its short life so far. Others place the initial mass closer to the current estimates, with less drastic early mass loss, but still substantial wind-driven shedding over the remaining main sequence lifetime. In each case, the star is expected to continue burning hydrogen in its core for only a few million years in total, a very short time compared with the lifetimes of lower mass stars. During this period, the internal helium enrichment and external mass loss proceed together, gradually transforming both the core and the envelope. As the main sequence phase advances, structural changes in the core and envelope can alter the star's position among its cluster companions. A more helium-rich core can sustain high luminosity, but may contract slightly, changing the temperature gradient and the way energy flows outward. The envelope may react by expanding or contracting in response, leading to changes in radius and effective temperature. At the same time, the wind may strengthen or weaken as surface conditions change, feeding back on the mass loss rate. Observationally, these changes might manifest as subtle shifts in spectral type or wind properties over timescales longer than current monitoring campaigns span. Within the cluster, where many massive stars evolve in parallel, such changes would gradually alter the distribution of temperatures and luminosities among the brightest members, but the overall impression of a brilliant core would remain during the main sequence era. After core hydrogen is exhausted, stellar evolution models predict that a star as massive as R136a1 would not simply stop shining, but would transition into later phases where helium fusion and subsequent nuclear burning stages occur in the core or in shells. These later stages involve changes in internal structure, the development of new burning regions and further mass loss that may strip away remaining hydrogen-rich layers. However, the details of these phases and the exact path that R136a1 will follow through them are sensitive to uncertain factors such as rotation binarity and the cumulative effect of earlier mass loss. For this reason, while models can outline general trends such as a move toward hotter, more compact, more chemically evolved states, the specific sequence and timescales remain less certain than for the current hydrogen burning phase. In the present description, the emphasis remains on the main sequence behavior because this is the phase that observations most directly constrain at the moment. The likely evolution of R136a1 also has implications for the surrounding environment. As the star continues to lose mass through its wind, it enriches the local bubble and the larger Tarantula Nebula with helium and nitrogen-rich material, modifying the composition of the gas out of which future generations of stars might form. As internal evolution proceeds, the wind's composition, and perhaps its strength, will change, altering the way energy and matter are supplied to the surrounding cavity. Over time, the cumulative effects of mass loss from all the very massive stars in R136 will shape the chemical and dynamical state of the cluster's environment, and R136a1 being among the most massive contributes strongly to this process. From the perspective of stellar physics, The life stage of R136a1 provides a valuable test of theories of very massive star evolution. Any successful model must reproduce the observed combination of extreme luminosity, effective temperature surface abundances, and strong wind while maintaining a hydrogen-burning core and a stable structure under the influence of radiation pressure. The evolution of such a model through the main sequence phase must also avoid episodes of instability or mass loss that would move the star away from the observed state too quickly. Different research groups explore such models with varying assumptions about rotation, convective overshooting, and mass loss prescriptions, and they compare the resulting tracks not only with R136a1, but also with other massive stars in R136 and in similar clusters. Taken together, these efforts build a picture in which R136a1 now occupies a main sequence position close to the upper mass and luminosity limits that theory allows with a large convective core and a radiation pressure-dominated envelope losing mass rapidly yet still firmly in a hydrogen-burning stage. Its future evolution, while not yet observed, is expected to involve continued core hydrogen burning for the remainder of a short main sequence lifetime, further mass loss that peels away outer layers, and a gradual shift toward more chemically evolved surface compositions, and possibly higher effective temperatures as deeper layers are exposed. Within the current narrative, it is sufficient to recognize that R136a1 is not static, but is partway along a predicted life path that theoretical models trace from its formation in the dense core of the cluster to more advanced phases. The star's present properties reflect this ongoing evolution, a core that is already enriched in helium compared with its initial state, an envelope shaped by radiation pressure and mass loss, and a wind that steadily transfers processed material and momentum to the surrounding nebula. All these aspects together define its current life stage as a very young yet already evolving extreme main sequence star in the heart of R136. From the vantage point of Earth, R136a1 appears only as a point of light blended with many neighbours in the crowded core of the cluster, yet from this distant unresolved signal, astronomers extract estimates of its mass size and wind by analysing how its light is distributed across wavelengths and how strong and broad its spectral lines are. The basic observational material consists of images and spectra, images taken through filters that isolate different parts of the spectrum, measure how bright the star appears at various wavelengths. Spectra spread the light into a continuous rainbow with absorption and emission features superimposed. For a star buried in a dense cluster, these data are hard-won. The angular separation between R136a1 and nearby bright stars is tiny, so the first step is to use instruments with very high spatial resolution, such as those on the Hubble Space Telescope, or large ground-based telescopes equipped with adaptive optics to separate the light from individual sources as cleanly as possible. Even then, some contamination from neighbours remains, and careful point-spread function fitting is needed to attribute the correct fraction of the measured flux to R136a1 itself. Once a reliable brightness is obtained in several filters, the next step is to correct for the effects of interstellar dust, which dims and reddens the light. Dust grains along the line of sight in the Large Magellanic Cloud and within the Tarantula Nebula absorb and scatter blue light more strongly than red. As a result, a hot blue star like R136a1 appears fainter and redder than it would if observed without intervening material. Astronomers measure the amount of reddening by comparing the observed colours of the star to the colours expected from a hot stellar atmosphere, or by using nearby stars with known spectral types as references. They then apply an extinction law, which describes how dust affects different wavelengths, to reconstruct the intrinsic brightness and colour of the star. This corrected brightness, combined with the known distance to the Large Magellanic Cloud, yields the intrinsic luminosity, the total energy output per unit time, once the appropriate geometric factors are taken into account. The distance itself is not measured for R136a1 individually, but is inferred from many independent methods applied to the galaxy as a whole, such as variable stars, eclipsing binaries, and geometric indicators. With a luminosity in hand, attention turns to the spectral energy distribution and individual spectral lines. The overall shape of the spectrum from ultraviolet through optical and into the infrared carries information about the effective temperature, while the strengths and ratios of specific lines reveal the ionization state and chemical composition of the atmosphere and wind. Because R136a1 has a dense expanding atmosphere, its spectrum is dominated by broad emission lines rather than the sharp absorption lines typical of less extreme stars. These emission lines arise as electrons in ions recombine and cascade down through energy levels in the accelerating wind, and their widths reflect the high velocities reached by the outflow. By fitting synthetic spectra from atmosphere models to the observed spectrum, astronomers can infer the effective temperature and surface gravity, which together with luminosity constrain the star's radius and mass. The radius is not measured directly as an angular size, but is derived from the relation between luminosity effective temperature and radius that follows from basic radiative properties. For a given effective temperature, a higher luminosity implies a larger radius. In R136a1, the atmosphere is extended and the wind is optically thick, so the radius that enters this relation is not the radius of a solid surface, but the radius of the layer from which most photons escape the pseudo-photosphere. Atmosphere models treat this extended structure and calculate an effective radius at which the continuum optical depth reaches a characteristic value. When the model luminosity and temperature are adjusted to match the observed flux and spectral distribution, the implied radius follows. The mass is then estimated by comparing the derived luminosity and effective temperature with theoretical stellar evolution tracks, which predict how stars of different masses move through the plane defined by these two quantities. For a given chemical composition and assumed rotation rate, a very massive star on the main sequence occupies a narrow range of luminosities and temperatures that increases with mass. Placing R136a1 on such a diagram allows an approximate mass to be read off by interpolating between tracks. Alternatively, the surface gravity inferred from atmosphere models, which depends on mass divided by radius squared, can be combined with the model radius to yield an independent mass estimate. In practice, both methods are used in combination and consistency between them is sought. The uncertainties in mass arise from several sources: errors in luminosity due to uncertainties in distance and extinction, uncertainties in effective temperature due to model assumptions and the complexities of the wind, and uncertainties in surface gravity due to degeneracies between line broadening mechanisms. Different atmosphere codes may treat line blanketing, clumping, and wind structure differently, leading to modest differences in derived parameters. In addition, the theoretical tracks used for comparison depend on assumptions about mix and overshooting and mass loss, so they too introduce model-dependent uncertainties. Despite these caveats, the consensus remains that R136a1 resides at the upper end of the mass distribution, with an initial mass likely well above 100 times the mass of the Sun, and a current mass somewhat lower after accounting for mass lost through the wind. The wind itself is characterized from the spectrum by analyzing the shapes and strengths of emission and absorption features. In a dense, expanding atmosphere, spectral lines often show profiles that encode the velocity field. P-Cygni type profiles, which combine emission with a blue-shifted absorption trough, reveal gas that both emits light and absorbs it along the line of sight as it flows outward. The terminal velocity of the wind, the speed reached far from the star, can be estimated from the extent of the blue-shifted absorption on the blue side of certain strong resonance lines in the ultraviolet. For R136a1 and similar stars, these velocities are found to be of order thousands of kilometers per second. The mass loss rate, the amount of mass carried away per unit time, influences the density of the wind, and thus the strength of emission lines that depend on recombination and free processes which scale with the square of density. By adjusting model mass loss rates until synthetic line strengths match observations, astronomers estimate how much mass the star is losing. However, as discussed earlier, if the wind is clumped, the same emission can be produced with a lower overall mass loss rate than in a smooth wind because dense clumps contribute disproportionately to emission. To account for this, models include clumping factors that describe how much denser clumps are compared with the average wind, and these factors are constrained by comparing diagnostics that respond differently to density. Even with such refinements, mass loss rate estimates remain uncertain by factors of order a few, but they consistently point to very high values compared with typical massive stars. The chemical composition of the wind is inferred from which lines are present and how strong they are. Enhanced helium and nitrogen line strengths together with weaker carbon and oxygen features indicate that material processed by the carbon-nitrogen-oxygen cycle has reached the surface. Atmosphere models with different abundance patterns are tested against the observed spectrum, and the set that best reproduces the line strengths is taken as representative. These abundance patterns in turn feed back into the derived mass and evolutionary stage because they signal how far the star has progressed in bringing internal fusion products to the surface. In this way, a consistent picture is built in which the observed luminosity temperature, gravity mass loss rate and abundances all correspond to a star of very high mass in a particular evolutionary phase. The inference of size and mass also accounts for the fact that R136a1 sits in a strong external radiation field created by nearby massive stars. In principle, external illumination can affect the appearance of a star's spectrum by adding background light, or by altering the ionization state of the outer wind. Models must therefore treat the atmosphere and wind as part of a local environment that includes the cluster's radiation field. Observational strategies help mitigate this complication by subtracting background nebula emission and by isolating the stellar spectrum as much as possible. Remaining systematic effects from the environment are accounted for in the uncertainties. Beyond individual spectra time series observations can in principle refine mass and radius estimates. For example, if R136a1 were part of a binary system with a companion of comparable brightness orbital motions, might cause periodic Doppler shifts in spectral lines or small changes in brightness as the stars eclipse each other. From such data, orbital parameters and dynamical masses could be derived. In the crowded core of R136, however, detecting such signals is challenging, and no firm dynamical mass measurement has yet been secured for R136a1. As a result, the mass remains an inference from atmosphere and evolution models rather than a direct dynamical determination. This limitation is openly acknowledged, and it is one reason why the exact value of the mass remains subject to revision as models and observations improve. Nonetheless, the general conclusion that the star's mass lies well above that of typical massive stars is robust. Putting all these elements together, the process of inferring mass size and wind properties from light is an exercise in constructing and testing self-consistent models. Observers measure fluxes and spectra, correct them for distance and extinction, and then use atmosphere and stellar evolution codes to derive the combination of luminosity effective temperature radius mass and mass loss rate that can reproduce the data, modifications are made for clumping rotation and chemical composition, and the results are compared across different codes and independent studies. Where different approaches converge, confidence grows that the inferred properties capture the essential physics. Where they diverge, the discrepancies highlight areas where the models need refinement or where new observations could be most informative. In the case of R136a1, this iterative process has gradually moved estimates away from the very highest masses once suggested by early, more blended observations towards somewhat lower though still extreme values as the core of R136 has been more finely resolved and atmosphere models have become more sophisticated. The star thus stands as an example of how much information can be extracted from a distant point of light and how that information depends on the interplay between observation and theory. Within the present understanding, the light from R136a1 encodes a picture of a very hot luminous wind-driven star with a large radius and a mass near the upper end allowed by current models, and the methods used to infer these quantities form a crucial link between raw observations and the physical description of the star that has been developed across the preceding sections. Observations of R136a1 across many wavelengths build a fuller picture of the star and its environment than any single band of light could provide, because different parts of the spectrum emerge from different layers of the atmosphere, wind, and surrounding nebula, and respond to different physical processes. In the ultraviolet and blue optical range, the star's radiation is strongest, and instruments that are sensitive to these wavelengths record the bulk of the flux that carries information about its effective temperature and ionizing power. In these short wavelength bands, the continuum resembles that of a very hot stellar atmosphere, rising toward the ultraviolet, while superimposed broad emission and absorption features reveal the structure of the dense high-velocity wind. Farther into the red and near-infrared, the continuum declines but remains bright enough that lines formed in cooler or more extended regions of the wind and nebula can be studied. At still longer infrared wavelengths, emission comes increasingly from heated dust and warm gas in the surrounding Tarantula Nebula, tracing how the star's energy is absorbed and re-emitted by the environment. Because Earth's atmosphere absorbs most ultraviolet light and distorts incoming wavefronts, observations of the highest energy part of the spectrum rely on space-based telescopes that operate above the atmosphere. These instruments record the ultraviolet spectra of the brightest stars in R136, including R136a1, and reveal strong resonance lines of ions, such as nitrogen, carbon, and silicon, with characteristic Piscini profiles that signal outflowing gas. The depth and shape of the blue-shifted absorption components show the terminal velocity of the wind, while the overall flux distribution constrains the effective temperature. Ultraviolet observations are especially important for measuring the ionizing photon output that cannot be observed directly, since photons energetic enough to ionize hydrogen are absorbed by interstellar gas before they reach the observer. By fitting models to the observed ultraviolet spectrum, astronomers estimate how many ionizing photons the star emits, and thus how strongly it contributes to keeping the surrounding hydrogen ionized. In the optical range, high spatial resolution imaging resolves the crowded core of R136 into individual stars as far as current instruments allow, and R136a1 appears as one of the brightest points. Narrow band filters centered on emission lines from ionized gas such as hydrogen, recombination lines, show the nebular glow around the cluster, while broad band filters measure the combined stellar light. Optical spectroscopy obtained with large telescopes that can separate the star's spectrum from that of its neighbors and from the nebula background provides detailed line profiles for helium, nitrogen, and other elements. These data, combined with ultraviolet spectra, feed into atmosphere models that must reproduce the full set of observed lines across the spectrum. In the near-infrared, observations penetrate more deeply through dust because longer wavelength light is less strongly absorbed and scattered by grains. This allows astronomers to study regions where dust obscuration is significant and to cross-check extinction estimates made from optical colors. Infrared spectra include lines from hydrogen, helium, and some metal ions that form under conditions somewhat different from those of ultraviolet and optical lines, giving complementary constraints on temperature, density, and wind structure. Infrared imaging also reveals embedded younger stars and warm dust structures in the Tarantula Nebula, helping to place R136a1 and its neighbours within the larger pattern of star formation and feedback. At mid-infrared wavelengths, dust heated by the intense radiation field around the cluster radiates strongly, outlining cavities, filaments and shells where stellar light and winds have cleared or compressed the gas. Beyond the infrared, X-ray observations probe the hottest plasmas in the region, which arise where stellar winds collide with each other or with denser clouds of gas. Space-based X-ray observatories detect both point sources and diffuse emission in and around R136. Some point-like X-ray sources are associated with individual massive stars whose winds produce strong shocks, while the diffuse component traces large volumes of shock-heated gas within the cavities carved by the cluster. The core region where R136a1 resides emits X-rays, but current angular resolution does not easily distinguish the contribution of any single star in this tightly packed area. Instead, models of wind collision zones and cluster-scale outflows are compared with the observed X-ray luminosity and spectra to infer typical densities, temperatures, and energy input rates. Even if R136a1's individual X-ray emission cannot be isolated, the presence of hot gas around the core confirms that the combined winds of the most massive stars, including this one, thermalize a significant fraction of their mechanical energy. Radio observations, though more challenging for such a distant and compact region, add further context by tracing free emission from ionized gas, and in some cases non-thermal emission from shocks or possible remnants of earlier massive stars in the wider nebula. In the immediate vicinity of R136a1, free radio emission from its wind may be present, but detecting it cleanly against the bright background of the Tarantula Nebula requires very high sensitivity and resolution. On larger scales, radio maps show the distribution of ionized and neutral gas around the cluster, indicating where dense clouds remain and where the ionization fronts driven by the cluster's radiation have advanced. These data complement the optical and infrared images by revealing structures that are opaque at shorter wavelengths or too cool to radiate strongly in the infrared. Multi-wavelength observations also help disentangle the roles of different massive stars in shaping the nebula. By comparing the spatial distributions of ultraviolet, optical, infrared, X-ray and radio emission, astronomers can identify regions dominated by stellar radiation, by wind-driven shocks, or by residual cold gas. For example, zones of strong mid-infrared dust emission may mark places where ultraviolet photons from stars like R136a1 are absorbed by grains and re-emitted, while adjacent cavities in radio maps may show where gas has been ionized and rarefied. Overlaying these maps with the positions of the brightest stars reveals how the most luminous cluster members line up with features in the gas. In many cases, 136a1 and similar stars lie near the centers of cavities, or the bases of bright nebular arcs consistent with their role as major sources of ionizing photons and mechanical energy. Teasing out the specific contribution of R136a1 remains difficult because of crowding. but the correlation between the core of R136 and the brightest nebula features supports the view that the central stars taken together power much of the observed structure. In addition to spatial mapping time domain observations across multiple wavelengths, can search for variability in the star and its environment. Changes in line profiles or continuum brightness in the ultraviolet and optical could indicate shifts in wind strength, surface conditions, or possible binarity, while variations in X-ray or radio emission might signify evolving shock structures. For R136a1, the available data have so far shown no large periodic changes attributable to the star itself, though the cadence and duration of observations are limited. This relative steadiness is in line with the picture of a star in a stable hydrogen-burning phase, but continued monitoring could refine this view and possibly reveal subtle variability. Multi-wavelength coverage also allows cross-checking of models. Atmosphere and wind models that reproduce ultraviolet and optical spectra must, when extended to infrared and X-ray predictions, remain consistent with observed fluxes and line strengths in those bands. If a model predicts too much X-ray emission from wind shocks, or too little infrared emission from heated dust, it may require adjustments in mass loss rates, clumping factors, or the geometry of the wind. In this way, data from different parts of the spectrum act as independent constraints on a single physical picture. Conversely, agreement across bands increases confidence that the essential parameters of the star and its environment have been captured correctly. For R136a1, the convergence of ultraviolet, optical, and infrared-based analyses on similar luminosities, temperatures, and abundance patterns supports the conclusion that it is an extremely hot luminous star with a strong clumped wind and a helium and nitrogen-enriched atmosphere. Remaining differences between studies often arise from how much weight is given to various wavelength ranges, or from how extinction and crowding corrections are handled. As new instruments with higher sensitivity and resolution become available, especially at infrared and X-ray wavelengths, they provide sharper views of the Tarantula Nebula and its clusters, including R136. Observations that better separate individual stars in the core, refine extinction maps on small scales, and measure faint spectral features add to the growing multi-wavelength picture. Within this picture, 136a1 remains one of the key sources whose properties must be matched. The star's presence is registered differently in each band as a dominant ultraviolet source, as a bright optical and near-infrared point, as a contributor to mid-infrared dust heating, as one of the engines behind diffuse X-ray emission, and as a likely source of free radio emission from its wind. Together, these observations show that no single wavelength tells the whole story. Instead, the multi-wavelength approach reveals a consistent but layered view in which the inner hottest regions of the atmosphere and wind are best probed in the ultraviolet and optical. The interaction with dust and cooler gas is traced in the infrared. The hottest shocked plasmas appear in X-rays, and the extended ionized gas is followed in the radio. Through this combined lens, 136a1 and its environment emerge not as a simple point source, but as a complex multi-component system whose different aspects are illuminated in different colors of light, all of them ultimately powered by the extreme energy output of the star and its massive neighbors in the core of R136. Behind the observed spectrum of R136a1 lies a complex web of physical processes that cannot be read directly from the data, so astronomers construct detailed computer models of the star's atmosphere and wind to bridge the gap between what is seen and what is physically present. These models aim to describe how radiation moves through the extended flowing outer layers, how atoms and ions are ionized and excited under intense radiation fields, and how the gas accelerates from near rest in the deep layers to high speeds in the wind. In their simplest form, atmosphere models assume that the star is spherically symmetric, and that conditions at each radius can be described by a set of physical variables such as density, temperature, velocity, and chemical composition. For a very massive hot star like R136a1, the models must handle a regime where the wind is strong, the radiation field is intense, and the gas is far from local thermodynamic equilibrium. This means that the populations of atomic energy levels and ionization states are not set only by the local temperature and density, but are influenced heavily by the radiation field itself. To capture this, the models solve the equations of radiative transfer, together with the equations that describe how atomic-level populations respond to radiation, and collisions a task that requires iterative numerical methods. In practice, the modelling begins with a guessed structure for the atmosphere and wind, an initial profile of temperature, density, and velocity as functions of radius, and a set of assumed abundances for elements such as hydrogen, helium, carbon, nitrogen, oxygen, and iron. Given this structure, the code calculates how radiation at many frequencies propagates through the gas, how often it is absorbed and re-emitted, and how the resulting radiation field affects the ionization and excitation of the gas. From the updated ionization and excitation state, new opacities and emissivities are computed, and the radiative transfer is solved again. This cycle repeats until the radiation field and the state of the gas are consistent with each other, and the outgoing spectrum stabilizes. The resulting synthetic spectrum can then be compared directly with the observed one. If the match is poor, the model parameters are adjusted and the process is repeated. For R136a1, this procedure must include a large number of spectral lines, because the heavy elements in the atmosphere and wind contribute many thousands of lines that overlap and interact, a phenomenon known as line blanketing. Line blanketing affects the emergent spectrum by redistributing energy from some wavelength regions to others, and by altering the temperature structure of the atmosphere. In a hot luminous star, the forest of metal lines in the ultraviolet can absorb photons and re-emit them at longer wavelengths, reducing the ultraviolet flux and increasing the output in the optical or infrared. Models that neglect line blanketing can therefore misestimate the effective temperature and luminosity. Modern codes include extensive atomic data for many ions, and account for the combined effect of these lines on the radiation field. This is particularly important for stars like R136a1, whose spectra show strong lines of helium and nitrogen, and whose winds are driven by radiation acting on metal ions. The velocity structure of the wind is another key ingredient. A common approach uses a prescribed velocity law that starts at a small speed near the stellar surface and increases smoothly to a terminal velocity at large radii. The shape of this law, together with the mass loss rate, determines the density profile of the wind through the continuity equation. In more advanced models, the wind structure can be calculated self-consistently by balancing the radiative acceleration against gravity and inertia, but even then, simplifying assumptions are needed to make the problem tractable. The presence of clumping small-scale density and homogeneities in the wind is treated through parameters that specify how much denser the clumps are compared with the average and what fraction of the volume they occupy. These clumping factors are tuned so that diagnostics sensitive to density squared processes, such as certain emission lines or radio-free emission, can be matched alongside diagnostics that respond linearly to density, such as resonance line absorption. In modelling R136a1, different groups may adopt slightly different clumping prescriptions, leading to different inferred mass loss rates, even when the same observed spectrum is used. Agreement across multiple diagnostics helps narrow down the plausible combinations. The chemical composition is adjusted to reproduce the relative strength of lines from different elements and ions. For instance, enhanced nitrogen and helium lines, together with weakened carbon and oxygen lines, signal the presence of material processed by the carbon-nitrogen-oxygen cycle. By varying the abundances in the models and comparing them with the observed spectra in the ultraviolet, optical and infrared astronomers infer surface composition patterns. These patterns then inform stellar evolution models which must produce similar enrichment at the observed stage of life. In this way, atmosphere and evolution models are linked. The atmosphere provides surface conditions, and the evolution code must achieve those conditions through internal burning and mixing. The atmosphere models also supply estimates of the mass loss rate and wind velocity that feed back into evolution calculations, because mass loss alters the star's mass and angular momentum over time. In addition to fitting the spectra of R136a1, the models must account for the fact that the star resides in a bright cluster. Nebular emission from the Tarantula Nebula and scattered light from nearby stars contribute a background that must be subtracted from observed spectra. If this background is not handled carefully, faint features in the star's spectrum can be misinterpreted. Modelling therefore proceeds hand in hand with careful observation reduction, where the contribution of neighbouring sources and nebular lines is removed as well as possible. Some atmosphere codes allow for an external radiation field to be included, so that the effect of neighbouring stars on the ionization state of the outer wind can be explored, although these effects are often secondary compared with the star's own radiation. The results of atmosphere modelling are not unique. Different codes implement the physics of radiative transfer and non-local thermodynamic equilibrium in slightly different ways, use different atomic datasets, and make different approximations about the geometry and time dependence. When applied to R136a1, these codes may produce synthetic spectra that agree with observations to similar degrees, but imply somewhat different underlying parameters such as effective temperature or mass loss rate. Comparisons between codes in which the same observational data are modelled by different groups help identify which differences are due to physics and which to numerical implementation. Over time, such comparisons have led to improvements in the treatment of line blanketing, clumping, and the coupling between radiation and hydrodynamics. For R136a1 early models that did not fully resolve the core or include as complete a set of lines tended to infer higher luminosities and masses. Later models using higher quality data and more sophisticated physics have revised these values downward while keeping the star at the extreme upper end of the mass spectrum. This evolution in inferred parameters illustrates how the quiet work of model refinement can gradually bring theoretical descriptions into closer alignment with the data. Beyond static atmosphere models, some studies explore how small perturbations in the outer layers might affect the spectrum. By introducing slight changes in the density or velocity field, or by allowing the wind to have modest time dependence, researchers examine how sensitive key spectral lines are to such variations. If the spectrum is largely insensitive to small deviations, the static models gain credibility. If it is highly sensitive, then time-dependent or multidimensional effects may need to be considered. For R136a1, the relatively small variability seen so far suggests that one-dimensional steady-state models capture the bulk properties reasonably well, even if small-scale structure and possible asymmetries remain unresolved. The atmosphere models are also connected to the interior structure through the boundary conditions they impose. At the base of the atmosphere, the models require a radius, a luminosity, and a chemical composition that are consistent with the output of stellar evolution calculations. Conversely, the evolution codes need mass loss rates, and surface abundances that are consistent with atmosphere fits. Iterating between these two levels of modelling allows a more coherent picture of R136a1 to emerge, in which the interior supplies energy and composition to the atmosphere, and the atmosphere channels that energy into observable radiation and mechanical outflow. In this picture, the atmosphere is not a thin passive skin, but a dynamic region where radiation and matter interact strongly, shaping both the emergent light and the rate at which mass is removed. Computer models thus form a bridge between theory and observation. They translate abstract physical parameters such as luminosity, temperature, mass, and composition into concrete predictions for line strengths, line shapes, and continuum fluxes. By adjusting these parameters until the predictions match the observed multi-wavelength spectrum of R136a1, astronomers infer the star's physical properties within the limits allowed by current data and physics. The process is iterative and cumulative. Each new set of observations, each improvement in atomic data, and each refinement in numerical technique feeds back into the models. Over time, the synthetic spectra align more closely with the observed ones, and the inferred picture of the star becomes more precise. In the case of R136a1, this quiet stepwise work has clarified that the star is indeed extraordinarily luminous and massive, but perhaps not as extreme in mass as early estimates suggested, and that its atmosphere and wind are shaped by a combination of intense radiation, strong line blanketing, significant clumping, and chemical enrichment from internal nuclear processing. Within the narrative of this star, the atmosphere models stand as a detailed, if idealized, representation of the outer layers, showing how the raw energy from the deep interior is filtered, redistributed, and finally released as the complex pattern of light that reaches telescopes across the electromagnetic spectrum. In the broader context of stellar physics, R136a1 holds a special position because it lies near the apparent upper end of the stellar mass distribution, so its properties give insight into how massive a single star can be and still exist in a stable hydrogen-burning state. Observations of young clusters in the Milky Way and in nearby galaxies show that stars form with a range of masses that can be described statistically by an initial mass function in which low-mass stars are numerous and high-mass stars are rare. In many environments, this distribution follows a power law at the high-mass end, with the number of stars dropping rapidly as mass increases. The existence of a star like R136a1, with a mass inferred to be well above 100 times that of the Sun, means that the initial mass function in R136 extends into a regime that few other known clusters reach. At the same time, the fact that even in this very massive cluster, only a handful of stars approach such high masses suggests that physical limits shape the extreme tail of the distribution. Theoretical work on the formation of very massive stars indicates that when a protostar grows beyond a certain mass, the radiation it emits during accretion can begin to impede the inflow of gas. As the luminosity rises, radiation pressure on dust and ionized gas in the accretion flow can push material away, creating cavities and outflows that make it harder for additional mass to fall onto the growing star. In a simple picture, this feedback would halt growth once the star reaches a mass where its radiation balances the gravitational pull on the infalling gas, setting an upper mass scale. In practice, the situation is more complex. Accretion can proceed through disks that funnel material inward along directions where radiation escapes more easily, and clustered environments can supply gas along dense filaments that are harder to disrupt. Numerical simulations show that under such conditions, stars can grow to very high masses, but the maximum achievable mass still depends on details of the accretion geometry, the surrounding gas density and the metallicity, which influences opacity and radiation pressure. For metallicities similar to that of the Large Magellanic Cloud, some theoretical studies suggest that stars might form with initial masses in the range of roughly 100 to a few hundred solar masses before feedback and instability significantly limit further growth. R136a1, with its inferred mass in this regime, sits precisely where these models are most uncertain, and so it provides an observational anchor for these ideas. Another line of reasoning about upper mass limits comes from the internal stability of very massive stars. As mass increases and luminosity rises, radiation pressure plays a larger role in supporting the star, and the luminosity to mass ratio approaches the values where envelopes become marginally bound. In such stars, small perturbations can trigger pulsations or enhance mass loss, and if these processes become too strong, they may prevent the star from maintaining a stable, main sequence structure beyond a certain mass. Models of stellar structure that explore this regime test whether stars above a given mass can find equilibrium configurations without developing large amplitude instabilities or unphysically high mass loss rates. R136 1. By appearing stable over the timescales of observation, and by having a strong but not obviously runaway wind, suggests that stars in its mass range can indeed exist in a quasi-steady main sequence state, but it does not yet reveal whether significantly higher masses are possible in nature, or whether this range already lies close to a practical limit. Empirical constraints on upper mass limits can also be derived by examining the highest masses found in different clusters and comparing them with what the initial mass function would predict if there were no sharp cutoff. By counting how many stars above a given mass exist in clusters of various total masses, and by seeing whether the most massive stars scale with cluster mass in a predictable way, astronomers test whether there is a universal upper mass cap, or whether the maximum stellar mass grows with the richness of the cluster. R136, with its large population of massive stars and its exceptional total mass, is an important data point in this kind of analysis. The presence of R136a1 and several other stars with very high inferred masses suggests that in this environment the initial mass function extends at least up to the mass range that these stars occupy. If theoretical expectations of a hard upper mass limit at lower masses were correct, such stars would be unexpected. On the other hand, if the initial mass function were allowed to extend indefinitely, even more massive stars might be expected in a cluster as rich as R136 than are actually observed, so the observed highest masses still hint at some form of limiting behavior. The formation pathway of R136a1 also connects to questions of upper mass limits. In very dense cluster cores, close encounters between young stars and protostars can lead to mergers in which two or more lower mass objects combine into a single more massive star. In this picture, the highest mass stars may not form solely through direct accretion onto a single protostar, but through a combination of accretion and mergers in the crowded center. If such mergers are common, then the maximum mass that can be achieved is influenced not only by radiation feedback on accretion flows, but also by the dynamics of the cluster core, such as the rate of close encounters and the efficiency with which merged stars can remain bound and cool back into stable configurations. R136a1, located in the tight group of the most luminous core stars, exists in a setting where mergers are plausible. Yet direct evidence for a merger origin is difficult to obtain, and current observations do not distinguish conclusively between formation by monolithic accretion and formation through mergers for this star. In both scenarios, the net effect on upper mass limits is similar. The combination of feedback and dynamics sets a practical ceiling on how massive a single star can become in a given environment. Whether R136a1 lies just below that ceiling or comfortably within it is still under study, but its mass and luminosity clearly test the margins of current theoretical frameworks. Comparisons with other very massive stars in different clusters and galaxies add further context. In the Milky Way clusters such as those near the galactic center, and in massive star-forming regions contain stars whose masses are also estimated to be near or above 100 solar masses, although with their own uncertainties and environmental differences. In other galaxies, young massive clusters show bright stars that may occupy similar regimes. R136a1 stands out among these because the combined high quality of the data, the relatively well-constrained distance to the Large Magellanic Cloud, and the intensive modelling efforts devoted to R136 make its inferred properties particularly influential in shaping discussions about maximum stellar masses. If future observations and models were to revise its mass significantly downward, the tension between theory and observation regarding upper mass limits would ease somewhat. If, on the other hand, more refined analyses were to confirm masses at the higher end of current estimates, the need to accommodate such extremes in formation and stability models would become stronger. The uncertainties themselves are part of the picture. They arise from the difficulty of disentangling blended light correcting for extinction, modelling complex winds and connecting atmosphere results with evolutionary tracks. Each of these steps carries errors that propagate into the final mass estimate. In discussions of upper mass limits, it is important to acknowledge these uncertainties explicitly because they determine how tightly R136a1 can be used to constrain theory. For this reason, many studies present ranges of allowed masses and explore how different assumptions affect those ranges rather than claiming a single precise value. Despite the uncertainties, certain broad conclusions are robust. R136a1 and its closest neighbours in the core of R136 occupy a region of parameter space where observed stars are rare, and where theoretical models predict challenges to stable structure and formation. The existence of such stars, supported by multiple independent analyses, establishes that nature is capable of assembling and sustaining objects with masses of at least order 100 solar masses in environments like the Tarantula Nebula. The lack of clear examples of stars with much higher masses in similarly rich clusters hints that at some point either feedback during formation or instabilities during main sequence life limit how far the mass can increase. Within this framework, R136a1 serves as both a data point and a boundary marker illuminating the regime where cluster statistics, formation physics, and stellar stability meet. As models of star formation and stellar structure continue to improve, they are tested against this case, and their ability to reproduce a star with properties like those inferred for R136a1 becomes one measure of their completeness. In the current stage of knowledge, the star stands near the forefront of empirical constraints on the upper masses that stars can attain, and its role in this context adds another layer of significance to the detailed description of its structure and environment developed in earlier sections. Many aspects of R136a1 are now described by consistent models and repeated observations, yet a number of important questions remain open, and these uncertainties guide much of the continuing work on this star and its surroundings. One of the central questions concerns the exact mass of R136a1. Current estimates rely on atmosphere models, extinction corrections, and comparisons with stellar evolution tracks, all of which carry uncertainties. Small changes in the assumed distance to the Large Magellanic Cloud, in the local dust properties along the line of sight, or in the treatment of line blanketing and clumping in the wind can shift the inferred luminosity and temperature, and thus the mass. Different modelling groups using different codes and assumptions obtain values that all place the star among the most massive known, but with a range that still spans several tens of solar masses. Reducing this range requires more precise extinction maps in the Tarantula Nebula, better constraints on the cluster's distance, and further refinements in atmosphere and evolution models, especially in how they treat the coupling between radiation and the dense wind. Closely connected to the mass is the question of how rapidly R136a1 rotates. Rotation affects internal mixing surface abundance's Wien geometry and the star's evolutionary path, yet the rotation rate of a distant unresolved star in a crowded cluster is hard to measure. Spectral line broadening provides some information, but in a wind-dominated spectrum line, widths reflect wind velocities and turbulence as well as rotation. Without clear photospheric absorption lines, the projected rotation speed is difficult to isolate. Indirect evidence such as the degree of helium and nitrogen enrichment, or the star's position on theoretical tracks that include rotation, suggest that rotation plays a role in mixing, but the exact rate remains uncertain. Determining whether R136a1 spins slowly moderately or near breakup speed would help clarify how efficiently it mixes internally, how it sheds angular momentum through its wind, and how it may later evolve. Another unresolved issue is binarity. In a dense core like that of 136 massive stars commonly form or evolve in binary or multiple systems, and such arrangements can influence both internal structure and observed properties. If R136a1 has a close companion of significant mass, the system's combined light might be interpreted as belonging to a single star, leading to an overestimate of mass. Conversely, interactions in a binary such as mass transfer or tidal mixing could produce surface abundance patterns and wind properties that differ from those of an isolated star. Searches for radial velocity, variations in the spectral lines of R136a1 and its neighbours, are hampered by the complexity of the wind features and the crowding in the core. So far, no unambiguous orbital signal has been detected, but the available data are limited and subtle, or long-period binaries could escape detection. Future observations with higher spectral resolution and more extended time coverage may help clarify whether R136a1 is truly single or part of a multiple system, and dynamical mass measurements from binary orbits would offer a more direct test of the model-based mass estimates. The presence and role of magnetic fields in R136a1 are also topics of ongoing study. In some massive stars, large-scale surface magnetic fields have been detected through spectropolarimetric measurements, and these fields can channel winds, create magnetically confined outflows, and influence angular momentum loss. For R136a1, no clear magnetic detection has yet been reported, partly because of the difficulty of obtaining high-quality polarimetric data for such a distant and crowded object. If a strong, ordered magnetic field were present, it could shape the wind into streams and loops rather than a purely radial flow, affecting both the emergent spectrum and the distribution of hot gas in the local environment. Even weaker tangled fields might influence the small-scale structure of the wind and the development of instabilities. Without direct measurements, models of R136a1's wind and atmosphere usually neglect large-scale magnetic effects, or treat them in a simplified way, leaving open the question of how important magnetism is for this particular star. Another area where uncertainties remain concerns the detailed clumping structure of the wind. Observational diagnostics suggest that the wind is not smooth, but the exact clump sizes, shapes, and filling factors are not uniquely constrained. Different combinations of clumping parameters can sometimes reproduce the same set of spectral features, leading to degeneracies between inferred mass loss rates and clumping strength. Additional diagnostics such as radio-free emission, infrared lines, or X-ray emission from wind collisions can help break these degeneracies, but such data are challenging to obtain for R136a1 specifically. Understanding clumping more precisely is important because mass loss rate estimates feed directly into stellar evolution models, and small changes in the assumed rate can lead to significant differences in the predicted future path of a very massive star. The formation history of R136a1 remains another open question. While it's clear that the star now resides in the dense core of a young cluster, the process by which it attained its mass is not directly observed. Did it grow primarily through accretion from a massive disk under the influence of radiation feedback, or did mergers between protostars and young stars contribute substantially? Simulations of star formation in dense clusters show that both channels can operate, but the relative importance of each depends on the initial conditions and the dynamical evolution of the cluster. Observational signatures of past mergers such as unusual surface rotation or specific chemical patterns are subtle and not uniquely diagnostic. As a result, the formation pathway of R136a1 is inferred from models of cluster formation and from the statistics of the most massive stars rather than from direct evidence. This leaves room for multiple plausible scenarios, each consistent with current data, but emphasizing different aspects of clustered star formation. The long-term evolution and final outcome of R136a1 are also topics of active research with important uncertainties. Stellar evolution models that include rotation mass loss and internal mixing predict that a star of this mass will eventually exhaust hydrogen in its core, move into phases where helium and heavier elements fuse in the interior and continue to shed mass through powerful winds. Depending on how much mass is lost during the main sequence and later stages, the star may enter a phase resembling a classical Wolf-Rayet object with a surface strongly enriched in helium and heavier elements. The final collapse could lead to the formation of a compact remnant, such as a black hole possibly accompanied by an energetic transient event. However, the exact mass of the remnant, the details of the collapse and the nature of any transient depend sensitively on factors that are not yet well constrained, including the total mass retained at the end of nuclear burning, the rotation profile at collapse, the role of binarity if present, and the interplay between mass loss and internal structure. Because R136a1 is still in a hydrogen burning phase, these later events lie outside the range of direct observation, and any description of them remains model-based and subject to revision. The impact of R136a1 on its surroundings over its full life also involves open questions. While current models show that its wind and radiation contribute strongly to the local bubble and to the larger feedback in the Tarantula Nebula, the cumulative effect over millions of years, including later evolutionary stages, has not yet been observed. The star's eventual death, whatever form it takes, will inject additional energy and newly synthesized elements into the cluster environment, but the distribution and mixing of this material and its incorporation into future generations of stars require simulations that combine stellar evolution hydrodynamics and cluster dynamics. Observations of older clusters that may have once contained similar stars can provide indirect clues, but connecting them with the specific case of R136a1 involves several steps that add uncertainty. More broadly, R136a1 is embedded in a network of questions about the population of very massive stars in R136 and in other clusters. How representative is it of stars at the upper mass end? Do other clusters in different environments with different metallicities or densities host stars of similar or greater mass? How do variations in metallicity, which change opacities and wind strengths, influence the maximum masses that can form and the ways those stars evolve. R136a1 offers one detailed case study, but building a comprehensive theory of very massive stars requires comparing it with analogous objects across the local group and beyond. Each new discovery of a candidate very massive star, and each improved measurement of its properties feeds back into this comparison and helps refine the broader picture. Observationally, progress on these questions depends on sharper images, more sensitive spectra, and better coverage across wavelengths and time. Future instruments that can resolve the core of R136 more finely measure fainter features in the spectrum of R136a1, or detect small variations in its light, and lines will tighten constraints on its mass rotation binarity and wind structure. At the same time, advances in computing and atomic physics will continue to improve atmosphere and stellar evolution models, allowing more detailed comparisons with data. For now, the star stands as a system where many parameters are measured with enough precision to support a coherent physical description, yet not so precisely as to close off further investigation. The remaining uncertainties are not gaps in an otherwise complete picture, but active frontiers where new observations and models are focused. In the ongoing study of R136a1, these open questions give direction. They frame the efforts to refine mass estimates, search for companions, probe rotation and magnetic fields, and connect the star's present main sequence state with its formation history and eventual fate, all within the broader setting of the dense luminous core of R136 and the Tarantula Nebula.